Question, how are unit vectors used to multiply vector quantities? First of all, I need to point out something. You know how with regular arithmetic, if you write 7 times 5, that equals 35? And if you wrote 7 times 5 like that, that would also equal 35?
Yeah.
That's not the case when you're dealing with vector quantities. There's different meaning for the multiplication when you use the dot symbol, and there's a different meaning when you use the X cross symbol. So with regular math, same meaning. But that's not the case with vectors. A dot B and A cross B are two completely different things. They do not mean the same thing. The first one here, when you use a dot like that, it's called the dot product. But when you do the dot product, the answer you get is a scalar quantity. It doesn't have direction. Therefore, the dot product is also known as the scalar product. The second one, vector A, and then the X symbol, vector B, that would be stated vector A cross vector B. That's known as a cross product. When you do the cross product, you end up getting another vector quantity. In other words, your answer has direction, and the direction of the answer is perpendicular to both vector A and vector B. So for now, all you need to know, when you do a cross product, the answer you get is a vector quantity. It has direction. Therefore, another name for the cross product, it's also known as a vector product. Now, I could give you guys the formulas for calculating the dot product and the cross product. I could give you the formulas like it'd be done in 5 minutes. And you can memorize the formulas, and you can become very, very good at applying the formulas. And then in time, if you practice them enough, you would start to get a gut understanding of the true meaning of the dot product and the cross product. But I want you to have that gut understanding right now. So I was actually brainstorming last night, like, how do I help you get a true gut understanding of the meaning of the dot product and the meaning of the cross product. And you know how sometimes when you understand something, it's one thing, but then when you really try to break it down and teach it to somebody else, it's another thing, you know? And I was trying to figure out how to unfold the material. And I was brainstorming on paper, and then finally it started to click. And in the end, just on the dot product alone, I end up writing out nine pages of notes.
What?
To help you understand and have that gut understanding of the dot product.
You're going to write all of the page notes on the board.
Yeah, and so are you in your book. Because many of you are going to go on to be physics majors or engineers, or you're going to major in other sciences, and you're going to run across the dot product and the cross product. And yeah, you'd be able to use the formulas, but you want to be the person who actually gets it, who understands what the deal is. So let's begin. On to page 2.
Okay. This is just the best one. There's a cross product.
So if you're taking the dot product, vector A dot vector B, you end up getting a scalar quantity that you get when you multiply the component of vector A that's in the direction of vector B. You take the component of vector A that's in the direction of vector B, and you multiply that by the magnitude of vector B. Now, at first you might not be following that, so just copy it down. But you know, let's talk about and show graphically like what this actually means.
Wait, Mr. Zelinsky?
Yeah.
What's the word between and the?
A scalar quantity that you get when you multiply the component of vector A that's in the direction of vector B and the magnitude of vector B. Which word?
Oh wait. Oh, I got it. Nice try.
That's halfway.
So let's say you have vector B going up this way, and you have vector A going up that way. Neither of them are on the, you know, in the direction of positive X or positive Y. They're both, you know, at angles. So given these two vectors, our mission is to find an expression for A dot B. Now, if we want to state what the magnitude of A is, we could use these symbols. But remember, for short, the magnitude of vector A, the length of vector A, we could just write A without the arrow sign. And the magnitude of vector B can be rewritten, just with the B without the arrow sign. So what we're going to have to do is we're going to have to break vector A up into components, but not horizontal and vertical components. We're going to have to break up vector A into components that are parallel with vector B and perpendicular with vector B. And we're going to do that by creating a little vector triangle where vector A is the hypotenuse. And there's one component that's parallel to B and one component that's perpendicular to B. So our mission at first is to resolve vector A into one component that's parallel to vector B and one component that's perpendicular to vector B. And we're going to do this by creating a vector triangle that has vector A as its hypotenuse. Here's a component of A that's parallel with B. I'm going to call that A parallel. Two little slanted lines. And then here's a component of A that's perpendicular to B. I'm going to call that A perpendicular. So now, what is A dot B? It's the component of A that's parallel with B times the whole shebang magnitude of B. It's as simple as that. It's a scalar quantity. It doesn't have direction. It's just a number and a unit. And how do you get that number? You take the part of A that's going in the direction of B, and you multiply that part of A with all of B. So I want to draw you 3 scenarios, and I want to ask you, in which scenario would the dot product of the vectors be the greatest? Which case would the magnitude of the dot product be the greatest? Peter, what do you think? Case 1, 2, or 3? My vectors A and B are supposed to be the same length in all 3 diagrams. I'm sorry if it's not. You see, here, all of vector A is parallel with B. So you would take all of A and multiply it by B to get the dot product. But here, you would have to break vector A down into parts. Part of A goes here, and part of A goes up that way, yes? And you would only want this little piece right there, A parallel. And you would multiply A parallel times B. Yes? And then this one here, how much of vector A is parallel with vector B? So guess what the dot product is going to be equal to in that case? 0. So in case 1, the whole shebang vector A would be multiplied by vector B, and that would give you the greatest magnitude for the dot product. Only a component of A would be used in number 2, and in choice 3, there's no part of A that's parallel to B, so the dot product would be equal to 0. So see if you can fill in the blanks of this statement here. Julie, would you read the statement, fill in the blank? Yeah. The greater the component of A that's in the direction of B, the bigger the answer is going to be for the dot product. In choice 1, all of A was going in the direction of vector B. In choice 2, only part of A was in the direction of B. And in choice C, there wasn't any of A in the direction of B. So that's the essence of the dot product. We're multiplying the part of the first vector that's in the direction of the second vector. Now, believe it or not, we've seen this before. We've actually calculated dot products last year. We didn't call it a dot product, but it actually is, and now we're going to formally go back and name it. Can anyone read your physics teacher's mind? What formula, what quantity did we calculate last year that was a dot product, actually? Jason? More... possibly, but that's not the quantity. That's not the essence. Good courage for answering. He said FG parallel, but that's not what I'm looking for. What quantity did we use a dot product? Where we found part of the thing of the first one in the direction of something else. Nikhil? Nope. All right. Torque was not a dot product. Yes?
Friction?
No, friction was not a dot product. We didn't use a component like that. Back to Jason. No, not momentum. Brad. No.
Did we just do it before, circulate?
When we calculated work, we were actually doing a dot product.
Oh, yeah. Yeah, because when I go like this,